Okay, let's get into this. We're taking a deep dive today into something really fundamental, but also kind of weird, about physics. The idea that time isn't, well, universal.
Right. It sounds strange, but your time, the time on your watch right now, it's absolutely correct for you.
But maybe not for someone else moving differently.
Exactly. That's the core from Einstein, really. Time depends on your reference frame, your motion. Every observer, you could say, gets their own personal clock ticking at its own rate.
So no big master clock for the universe then. How do we even talk about this?
Yeah.
Our source material, these notes from Andrea Menini, they mention two specific terms.
Yeah, they do. First, there's proper time. We use the Greek letter tau. Tau for that.
Okay, tau. And that's the time measured by someone or something like a clock.
Yeah.
That's moving with the object or event we're watching, like an astronaut's own watch on a speeding spaceship.
Perfect example. That's tau. Now, contrast that with laboratory time, which we just call tellers. This is the time measured by the observer who's, well, stationary, standing still, back in the lab or on Earth, watching that spaceship fly by.
Right, stationary observer time is tellers, moving observer time is pow.
And here's the kicker. If that spaceship is really moving fast, like approaching the speed of light, the astronaut's proper time, tau, actually runs slower than the laboratory time, tau measured back on Earth.
Hang on, slower. So if the astronaut experiences 1 second passing.
Then more than 1 second, maybe much more, has passed for the person on Earth watching them.
Wow, okay. So how are these two times in tau actually connected? Is there like a formula for this?
There is, and it's really elegant. It's the heart of time dilation. The equation is
Gamma dot tau.
gamma tau. Let's put that down. Tau is the lab time, the stationary observer.
Correct, the longer time.
And tau is the proper time, the moving observer, the astronaut.
Shorter time, yes.
And gamma, what's that symbol? That's gamma. It's called the Lorentz factor. And it's basically the stretching factor for time. It tells you how much slower the proper time runs compared to the laboratory time.
And this Lorentz factor, gamma, it depends on speed?
Critically, it depends explicitly on the velocity, velar, of the moving object compared to speed of light. The formula itself shows that as Bill gets bigger and closer to 2, gamma gets bigger too.
So faster speed means a bigger gamma, which means gamma gets even larger compared to tau.
Exactly. The difference between the two times widens dramatically as you approach light speed.
What about the extremes then? Like if you're not moving at all?
Then gamma is just 1, so the equation becomes tau to E1 or just tau. Your proper time and the lab time are identical. No difference. Makes sense.
Yeah, that checks out.
Yeah.
But the other extreme, if files gets incredibly close to tau,
Then gamma, the Lorentz factor, it shoots towards infinity.
infinity. So tau becomes infinitely larger than tau, meaning the astronaut's time would almost stop relative to us back on Earth.
Pretty much, yes. It would slow to a crawl. The source gives a great example. A spaceship at 80% the speed of light.
Okay, 0.8c, what happens then?
For every single second of proper time, tau that ticks by on the astronaut's clock. 1.67 seconds of laboratory time. Tau pass back on Earth.
Wow, nearly 70% longer. And this isn't just, theoretical noodling.
Oh, no, absolutely not. This is experimentally verified over and over. We see it with incredibly precise atomic clocks. You put one on a fast airplane or satellite and compare it to one on the ground.
And the moving clock runs slightly slower, just like the equation predicts.
Exactly. Even GPS satellites need constant correction for this effect. Otherwise, our navigation would drift off course pretty quickly.
Okay, that's clocks. Any other proof?
A really compelling one is muons. These are unstable particles, sort of like heavy electrons, created when cosmic rays hit our upper atmosphere. They have a known, very short lifespan, their proper time, tau.
Oh, sure.
About 2 microseconds, 2 millionths of a second. And they're created miles up.
So classically, they shouldn't have nearly enough time to reach the Earth's surface before they decay.
Correct. At nearly the speed of light, they can travel maybe a few hundred meters in their lifespan. But they're created many kilometers up.
Yet, we detect them down here.
We do. Loads of them. Because they're moving so incredibly fast, their internal clock, their proper time tau, is drastically slowed down relative to our laboratory time tower. That tiny 2 microsecond lifespan gets stretched, from our perspective, allowing them to survive the journey down to the surface.
So their time dilation lets them live longer in our reference frame.
Precisely. It's a direct, everyday confirmation of gamma tau. Time is relative.
So wrapping this up, the big takeaway is just undeniably that the faster you move, the slower your time progresses relative to someone watching you who's stationary.
That's the core of it. Motion fundamentally changes the flow of time.
And you mentioned this has knock-on effects, something about velocity and momentum.
Right. Think about it. If time itself isn't absolute, if time and dollars can be different, then basic concepts from classical physics that rely on absolute time start to break down, like momentum, usually mass times velocity. But velocity is distance over time. Which time do you use? Or tau?
Ah, I see. You can't just use the stationary observer's time if the object itself is experiencing time differently, Tom.
Exactly. You have to use relativistic definitions. Our sources mention the relativistic quantity of motion. It's a whole different way of calculating momentum and energy that accounts for time dilation and also length contraction and the increase of mass with velocity. It shows how deeply interconnected space, time, mass, and energy really are in Einstein's universe. It really makes you think, doesn't it? How something as basic as how fast you're going gets incredibly complicated once time itself is flexible.